Okay, I wanted to give you guys some feedback on a couple different um, pieces, mainly one piece in the experiment titled Uncertainty um, as it relates to data table 4 and the graphs associated with it. So, and this is my first go at it. So with this video, I'm doing this from home and I'll try and use my laser because I have to move the video camera around, so bear with me. So the first bit of information you were supposed to get was you're supposed to get values of t squared as it relate to this equation here. The data table basically gave you everything for y, and then you went on and found y bar, so that was just an average, and you filled that in and graphed it. So this was the graph of a free falling object. If you were to drop a rock or a ball, something with little to no resistance, this is about where it would be as it relates to time in terms of distance from displacement. So initially it would start here, and then after a half a second it would be at about 2 meters, and then after about 3/4 of a second it would be roughly around 3 meters away, so on and so forth. You'll see this expansion as time goes on. And then what you had to do also in the chart was you had to figure out what t squared was, and that was just simply by squaring the values of t that were on the left side of the chart. So for example, one value of t was 0.5, and to square that you would have gotten 0.25. And so we do what's called a linear regression on this equation y equals 1/2 gt squared. And it's basically just a little trick for us to try and make some sense of what's going on. These parabolic shapes, um, second degree equations which graph in the parabolic shape, um, sometimes don't give us all the information that we would like. Most of us already have worked with lines, so it's a little bit easier to work with. So we kind of play around with the information that's given here. So we're actually graphing a derivation of this, which I'll go into in just a second. So this does not represent this equation here. It represents the slope of a line. And that line looks like, here's my recreation of this on the left side here. On the right side is a little bit more information. So I'm trying to hold this camera steady so you can read it. So instead of 1/2 gt squared, we're going to use a linear equation, y equals mx plus b. That's the point slope form of a line, where m is the slope and b is the y-intercept. And instead of using x, we replace x with values of t squared. You'll see that in just a second. And instead of b, for this particular one, b turns out to be 0. And so m matches up with 1/2 g. We can figure out the slope pretty easily of a line, and we can calculate the slope of this line. So what I did was I picked off 2 points that were on but not, well, here we go, sorry, on but not near the line, hopefully on the line, but not too close to one another, sorry. And I used 0.25, 1.3, and 1.6, 7.8, and I used that in my calculation over here. So I can see that the slope is 4.8, and because we said that the slope matches up with 1/2 g, g being the acceleration due to gravity, the experimental value that I got is about 9.6, which isn't that far off from what we know. We know that the acceleration due to gravity is about 9.8 meters per second squared. So here is how we set this up. So again, we just match up these components. So instead of the 1/2 g, we replace that with the slope, and instead of t squared, you replace it with x. The b piece goes away. So just set all this stuff right here equal to one another because we already did this match, and you should be able to come up with information similar to this. You may not get this exact number, but it should be somewhere in the range, plus or minus, I would say 0.4 would be reasonable. But it all kind of depends on how you created this line and the points that you use. So good luck with that. Actually, you've already probably turned this in, but we'll make some corrections as we go down the line because we will be using linear regression in future experiments.